Hello and welcome to the Interference Technology webinar, EM Field Theory and 3 Types of EM Analysis. My name is Belinda Stashukevich and I'm the editor of Interference Technology. Established in 1970, Interference Technology helps EMI and EMC engineers find solutions to their various testing, design, application, and regulatory issues by publishing articles, news, and other practical content. This webinar is presented by Keith Armstrong. Keith graduated from Imperial College London in 1972 with a Bachelor of Science in Electrical Engineering, specializing in analog circuit design and electromagnetic field theory. He formed Cherry Clough Consultants Limited in 1990, which provides design services to help achieve compliance with EMC. They currently have 800 satisfied customers in almost all areas where electronics are used. This webinar is the first in a new series following the success of Keith's cost-effective EMC design by working with the Laws of Physics webinar, which took place on November 27, 2012. Hopefully many of you attended this previous webinar. If not, it is available for viewing on our website, interferencetechnology.com, and we encourage you to check it out. Now a word from our sponsor. Today's webinar is sponsored by AR. In the world of EMC, wireless, and beyond, AR is one company with infinite solutions. From broadband, high-powered solid-state amplifiers to complete conducted immunity and EMC test systems. Visit www.arworld.us for details on new products and accessories for your EMC testing needs. This webinar will be interactive. You will be able to ask questions and answer polls, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the blue box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. And to maximize the screen, click the middle button. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Now Keith will begin the presentation.
Hello. Oh, okay. Well, I gather many of you attended the webinar we did on the 27th of November, and this is really an expansion of that. And it comes in three webinars. This is number 1. And you can see the contents page just has 1 to 4. Later on we'll fill in the rest. Just a bit of background. I did electromagnetic field theory at university in my final year, passed all the exams. In real life, when I got my first interference problem, I pulled out my college notes, couldn't find one thing in those notes on EM field theory that related, not one word, to the problem that I had. Now, we're about 40 years later, 41 actually, 41 years later, and I'm going to talk about electromagnetic field theory. But I'm going to talk about the stuff that I've found over the years is what you need to do EMC design cost effectively. And when you do EMC design cost effectively, you also do signal integrity design, power integrity design. You save time and money, you get to market quicker, your products break down less in the field. The performance is better, the functional performance is better. It's all good, okay? So these are secrets I'm letting you into. That's taken me at least 22 years to figure out. And you'll wonder why afterwards, no doubt. Anyway, here we go. Every non-DC voltage or current is actually a wave of propagating electromagnetic energy. Now think about that. It doesn't mean that our electronic signals and power are electrons shuffling down a wire or a PCB trace. That's not what happens. If you took a mile-long cable, connected one end to a battery and a switch and the other end to a light bulb, if you threw the switch, the light bulb would light almost instantly, even seen from a mile away. But what do you think the speed of the electrons are in that DC circuit? It's actually about walking speed, about 3 miles an hour. So it's not the electrons, okay? It's really a propagating electromagnetic wave. That's what. Now, electromagnetic waves spread out and create electromagnetic fields. If you imagine throwing a stone into a pond, and you can see that there's a wave front that spreads out across the pond, and behind it is a pattern on the pool. Okay, so we have the wave front, we have the pattern. The pattern is what we call electromagnetic field. We measure fields in terms of field strength, which we'll talk about in a minute. Designing for EMC cost effectively is mostly about controlling fields. And his key issue here, these are all key issues, but the point is where we want our power or signals to be on a printed circuit board, in a cable, in a load, wherever, then we want to have high field strengths. Everywhere else we want low field strengths. Okay, so we're field shaping, if you like, controlling fields and waves. So they're high where we want them and low where we don't want them. This sounds complicated. In fact, it isn't really. But you have to understand what you're doing. The thing with a wave is it has different amplitudes along its path. That's why it's called a wave. When your conductor is long enough, it cannot have the same voltage or current at the same time along its whole length. And this is why when we get to higher frequencies, our circuits seem to behave so weirdly. You can probe a trace at one point and it seems to have one kind of signal on it. Probe the same trace at a different point, has a different kind of signal on it. And we throw our hands up and say, oh, this is so weird, you know. But it's not really. And hopefully you'll understand why, at least in essence, by the end of today. Yeah, I was going to say something else, but I've forgotten. The ratio between wavelength, which we call lambda, the Greek letter lambda, and the conductor dimension is very important then in EMC design. As a rule of thumb, a guideline, we can usually ignore wave effects when the dimension we're concerned with is less than 1/100th of the wavelength. We can totally ignore them in that situation. Not always, but usually. What does this mean at a gigahertz? It means less than 3 millimeters in the air. For a wire in the air, it's a bare wire in the air, because for a wire in air, the wavelength is 300 millimeters at a gigahertz. In a PCB trace, the wavelength is somewhat shorter, about a half, for reasons we'll talk about in a minute. So we're looking at about 1.5 millimeters, about the length of a via hole on an ordinary PCB. So anything longer than a via hole, or via hole if you prefer, we start to get nasty wave effects. And of course, many of you will already be testing things at more than a gig, more than gigahertz. 3, 4, 5, 6 gigs is common these days. 18 gigs, 40 gigs in some applications. And the corresponding length to which you can ignore wave effects is correspondingly smaller. And like I said, electric and magnetic fields, well, I said electromagnetic fields, but you can see where they come from, is the true nature of electrical and electronic power and signals. They both depend on the physical routes taken by what we think of as the send and return currents, what we design for. Okay? A huge amount of EMC, good EMC design, depends on controlling the path of the return current. Important point here is that all currents always flow in complete loops. There's no current ever that can, for instance, flow down a ground wire and disappear. Doesn't happen. It can't happen, never has happened. So the currents flow in loops that take the path of least impedance. That's usually the path with the least area, which usually means that the return current flows as physically close to its send current conductor as it's allowed to by our design. You may remember in the previous webinar on November 27th, I said that we often complain that the emissions from our products, and we think that they're malign in some way, they're trying to work against us. In fact, whatever arrangement of conductors you create with PCBs and cables and metalwork and what have you, you always get the smallest field pattern with the least emissions that that design is capable of, because that's how the laws of nature work. They're always trying to minimize field energy. So you only have yourself to blame, or we only have ourselves to blame, if we've got emissions that are too high. Going on a bit, you may breathe a sigh of relief here, because at this point people usually start hauling out Maxwell's equations. Well, they're not very helpful. You know, you can't do anything with them really, except get a few insights which are contained within this webinar anyway. So we need a few concepts. A fluctuating voltage creates an electric field, and a fluctuating current creates a magnetic field, which we call H. We measure electric fields in volts per meter, magnetic fields in amps per meter. At low frequencies, people sometimes measure magnetic fields in Tesla or Gauss or lines per centimeter or something like that. But in radio frequencies, in EMC work, we're almost always working in amps per meter. Electromagnetic waves, of course, have some power, P, which we call P. If they didn't have any power, they wouldn't be any use, would they? You know, our signals wouldn't do anything, our power wouldn't do anything. We measure power in watts per square meter for an electromagnetic wave in the air, which is the rate at which energy passes through an area. Now, we don't normally bother with that in EMC. It's more of an issue when you're trying to decide if the cell phone you just designed is going to fry somebody's brain when they hold it close to their head. Hopefully it won't. Permeability, which we call mu, and permittivity, which we call epsilon, or sometimes we call permittivity the dielectric constant, are important things. Fact is, all media or materials, including the vacuum, everything in this universe has conductivity or resistivity, whichever you prefer. In other words, a loss of electromagnetic energy as it turns it into heat. Although, if you've got a cubic mile of vacuum, it's hard to see how much conductivity it has. But everything has permeability and permittivity. In vacuum and air, pretty much, we have mu naught, the vacuum permeability, 4 pi times 10 to the minus 7 henries per meter. Henries, of course, is how we measure inductance. And this means the vacuum, the air, the space between the stars, can contain magnetic field energy. It has the characteristics of magnetic field energy. And also, we have epsilon naught, the vacuum permittivity, 1 over 36 pi times 10 to the minus 9 farads per meter. So the vacuum and everything in it has the characteristics of electric field energy too. Energy is actually stored in the vacuum in these fields. When we look at other media materials, we might be interested in FR4 or PVC round a wire or whatever, or steel in a housing, then we find we characterize their relative permeability and relative permittivity, mu r and epsilon r, as just bold numbers, just dimensionless numbers. Like steel may have a permeability of 400, not 400 anything, just 400, and FR4 has a relative permittivity of about 4 megahertz. That's actually more like a gigahertz. So we can say the absolute permeability of any material is its relative permeability times the vacuum, and the absolute permittivity, or dielectric constant, is the relative permeability times the vacuum permittivity times vacuum permittivity. Sorry. Where we have conductors, wires, PCB traces, lead frames, etc., permeability and epsilon, mu and epsilon, are what causes them to have inductance and capacitance, which we call L and C. What this means is whenever we have a fluctuating voltage, V, we always have an associated current, I, and vice versa. Whenever we have a current, we always have voltage. There's no way of having one on their own. Even you might have a little test pad, a 2 millimeter square test pad attached to an otherwise unconnected pin of a ball grid array or something, and all it has is a voltage on it, you think. But no, there's a current required to charge up and discharge the capacitance of that pad. Some digital circuit designers have been known to think that because their digital circuits have a low impedance output, but the digital gates have a high impedance input, maybe 10 megohms or something. Therefore, when they put a voltage on a trace, they just waggle the voltage around and there's no current in it because the load is so high. This isn't true. There's a significant capacitance associated with the gate, about 3 or 4 picofarads. Doesn't sound like a lot, but it is. And there's a significant capacitance associated with the trace. So whenever we vary the voltage on the trace, we have to supply some current. And for the edges that we use these days in digital circuits, that current can be measured in tens or hundreds of milliamps just to charge the trace up, which creates magnetic fields, of course. In insulators like air, plastic, fiberglass, whatever, permeability and permittivity cause effects similar to inductance and capacitance. Like I said, the vacuum or the air will store electric field energy or magnetic field energy, and vice versa. Whenever we have an electric field which is fluctuating, not DC, there's always an associated magnetic field with it, and vice versa. You can never have one without the other. Of course, if I was to talk about the inductance of the vacuum, then the purist would laugh at me. So I don't say that. I just say it's a similar effect. Permeability and permittivity are just properties of the universe that we find ourselves in. It's no good asking where they came from, or what causes them. They are what causes other stuff. One of the things they govern, one of the things they cause, is the propagation velocity of electromagnetic waves, and also the electromagnetic waves impedance. In the far field, we'll look at that near field, far field in a minute, the impedance of a wave is the ratio of its electric and magnetic fields. That's volts per meter divided by amps per meter. And the per meter cancels out. So the impedance of a wave in the air, or in the vacuum, is volts over amps, which means it has dimensions of ohms. Some people call that Ohm's law for electromagnetic waves, which is a nice sort of expression. In fact, what governs the impedance is the square root of the permeability divided by the permittivity. In air or vacuum, it's just mu naught over epsilon naught, which works out to be 120 pi. Being engineers, we call it 377 ohms because it's close enough. In a medium or material, which has a relative permeability or relative permittivity which isn't 1, then we get a different impedance. If we've got a high permeability and a low permittivity, we can get higher than 377 ohms. And if we have it the other way around, with a high permittivity, lots of capacitance, and a low permeability, we can get less than 377 ohms. In the air, in the far field, is 377. The velocity of the wave's propagation. See, this sort of issue is necessary for designing shielding. For velocity of waves propagation, which is important for knowing the wavelength, and you'll see later on, well, wavelength is very important for designing anything to do with EMC. We need to know the velocity. The velocity is actually 1 over the square root of the permeability times the permittivity. For the vacuum or the air, it's nearly 300 million meters per second, the speed of light. In a material which has relative permeability or permittivity, it's 300 million meters per second divided by the square root of mu r epsilon r. So whenever we have permeability or permittivity, the velocity is always slower. Nothing can go faster than the speed of light in the air. I should say information can't travel faster, but that's really going beyond our remit here. So why are we interested in velocity? Well, I mentioned before, because we want to know the wavelength. V equals f lambda. The velocity equals the frequency times the wavelength. We're generally speaking in EMC, we're measuring frequency. All our specifications are in frequency. Well, the continuous RF ones are anyway. And we want to know the wavelength in order to decide whether a trace needs to be treated like a transmission line or whatever. and they're tied together by the velocity. But the velocity varies, of course. In air, it's 200 millimeters a second. It's sometimes called c, which Einstein made famous with his E equals mc squared. C is the speed of light in the vacuum. It's actually quite slow. It's 3 nanoseconds per meter. 3 nanoseconds per meter. You know, you can do lots of digital calculations in 3 nanoseconds these days. So the speed of light is a bit of a problem. With modern electronics, it's a bit like trying to shove your gigabits per second through treacle, but it's what we have to work with. In media or materials which have permeability or relative permittivity greater than 1, velocity is always slower. So the wavelength is shorter for a given frequency. In a printed circuit board, trace velocity is about a half of c because the permittivity is about 4 in FR4. In some other materials like Teflon, it might be 2 or 3, for instance. But in a ceramic substrate, like on a hybrid, thick film hybrid circuit, it's about 10. And the wavelength is very short, about a third. Anyway, the wavelength in a PCB made of FR4 is about half of what it would be in the air, which is why earlier on we said 1/100th of a wavelength at a gigahertz was 1.5 millimeters, not 3. I mentioned far field. We need to talk about that. Near to a fluctuating voltage or current in our circuits or on our metalwork, the electric and magnetic fields have complex field patterns. I could write the equations down for you, but all we would say is, well, look, there's a 1 over r cubed term, there's a 1 over r squared term, there's a 1 over r term. You know? R being the radial distance away from the source. We're assuming here a point source. This tells us a little bit about EMC equations. When did anybody ever have a point source? You never did. You have to integrate all these point sources along the length of your wire, and it soon gets a bit tedious, which is why the simple equations never really work unless you've got a very simple situation. A wire in a box, perhaps. We can think of these 1 over r cubed, 1 over r squared terms as stray capacitance and stray mutual inductance. Actually, the other way around. The r cubed is usually the inductance, and the r squared is the capacitance. Stray electric and magnetic field coupling. Far enough away from our source, you know, so that it looks tiny. No matter how big it is, if you're far enough away that it looks really very small, the fields become electromagnetic waves. Plane waves, we call them. And they have electric and magnetic fields in the ratio of their wave impedance in that medium, Z. And they have a simple spherical distribution. And the field strength varies as 1 over r. Now, we're all familiar with tests, emission tests, where you have a choice sometimes of testing at 10 meters or at 3 meters. And you can take the limit at 10 meters and add 10 dB and use it as a limit at 3 meters. I know it's a bit crude. And people argue about whether it should be 8.5 or 11.1 or whatever. But anyway, it's a spherical distribution, or hemispherical in the case of a measurement over a ground plane. The field strength varies as 1 over r. Or you might take the 3 meter limit, if that's what you've been given, and measure at 10 meters with a limit line reduced by 10 dB. We're in the far field, and a lot of the measurements of fields above 30 megahertz are carefully designed to be in the far field because they're more reproducible that way. Here's an example of a 3D field solver simulating a heatsink. It swept through the frequency range and found its resonant frequency at 5.32 gigahertz. It's only a little heatsink. And this is the field pattern shown in 2 dimensions of a slice through the heatsink. There's a little wire, which is what the simulator says is injecting the current into the heatsink, which is the power transistor switching voltage through the stray capacitance of its thermal pad, a current into the heatsink. Now you can see how in the near field there's areas of very low field, like, you know, purple, very low field. There's areas of very high field in red, and there's green and yellow and blue fields around. And it's around this sort of area, it's very complex. This is the near field. But you can see how As we go further away, it's all settling down somewhat. This is a heat sink over an infinite ground plane with nothing else anywhere nearby. Of course, in real life, there'd be other metal things nearby to distort the field. But anyway, far enough away, it's looking like just a hemispherical emitter. This is the r cubed, 1 over r cubed, 1 over r squared region. Further away, it's just the 1 over r region. We have a couple of equations that tell us where to draw the line between the near field and far field. If we have a source which is much smaller than the wavelength at the frequencies we're interested in, then the boundary between the near and far field is lambda over 2 pi, roughly a sixth of the wavelength. So the higher the frequency, the closer the near field, far field boundary is. But if we have sources which are large compared with the wavelength, and this is almost anything if you measure it at 18 gigahertz, for instance, where the wavelength is only about, what? About 20 millimeters or something. A bit less than that. The near field, far field boundary is 2d squared L lambda, where d is the largest dimension. We don't care about d if it's much smaller than the wavelength, but if it is bigger than the wavelength, then we do care about it. Notice that the lambda now is on the bottom. That means that the bigger the thing gets, the bigger d gets. Or let's put it this way, the smaller the wavelength gets, the further away the near field, far field boundary is. So if your source is small and the frequency increases, the near field sucks itself in. If your source is large and the frequency increases, the near field extends, gets bigger. Let's look at the case which is often true for small things at less than a gigahertz. We have the wave impedance versus radial distance from the source. There's an E-field source, which, if you imagine, if we could somehow measure a point source with a point measuring instrument, we'd see it had an infinite impedance, but we can never do that in practice. A magnetic field source, a pure magnetic field source, measured as a point, has a zero impedance, but we never get there, of course. As we get further away from the source, this might be a decoupling capacitor on a circuit board, decoupling an IC. This might be the test pad I mentioned earlier. As we get further away from them, they settle down to much the same sort of impedance. So we end up with this. In the case of the air, we end up with them settling down to 377 ohms. Regardless of what they were when they started off, they settle down to 377 ohms. If they were traveling in oil, say we're interested in, I don't know, some big oil tank for some reason, then that impedance would probably be more like about 150 ohms, 180 ohms, because of the dielectric constant of the oil being about 3. And you can see now why I use such weird units for the bottom axis. These are units of lambda over 2 pi. So I could show that at lambda over 2 pi, 1 on this scale, we say, oh, these are so close now, whether they're from an E field or an H field source, they're so close together that we can say we're in the far field. This is the near field, where we have complex fields like we saw around that heat sink a minute ago, and this is the far field, where we have plane waves. This is stray capacitance, stray mutual inductance, which is what's called the induction field sometimes. Okay, it's time for some poll questions to see if you're awake out there.
Thanks, Keith. Attendees, we'd like to ask you a poll question. Please answer the following question. How do a signal's voltage and current vary along the length of a PCB trace or cable? They remain the same values all along its length. They depend on how the transmission line is terminated, or they depend on the wavelength of the signal. We'll give you a few seconds to answer this question. Many of you are voting. About half of you have voted, and it appears that C is the overwhelming majority, and that is correct.
Good for you.
We also have another poll question. At what speed does an electromagnetic wave propagate in any medium, like air, plastic, oil, etc.? About 300 million meters a second, or depends on the mu and epsilon of the medium? Please answer this question. We'll give you a few seconds. Most of you have voted and picked B, which is the correct question. Back to you, Keith.
Right now it makes me wonder whether people are sitting there thinking, when's he going to say something interesting? You know, I know all that. Anyway, let's hope there's something interesting coming up now. We have three types of EMC analysis that we use. When we have conductor dimensions in 3 dimensions, less than a sixth of the wavelength at the frequency we're concerned with, we can pretend we can use lumped circuit analysis. Basically, we say it has so many nanofarads, so many picohenries, you know, so many milliohms, microohms, megohms, whatever. Just basic numbers. So we might say, if we have a little 10 nanofarad multi-layer ceramic decoupling capacitor, we might say, well, it's got 10 nanofarads, it's got 3 nanohenries, self-inductance, and it's got about 7 milliohms because it's an X7R capacitor. And as long as it's small enough, we can say that. But we also have to take, oh, I'm getting ahead of myself here. When conductor dimensions are bigger than a sixth of the wavelength along one axis alone, we can use transmission line analysis. And this is based on the telegrapher's equations. Invented in America, when they started stringing wires up to send telegraphs to try and put the Pony Express out of business, which they did quite quickly. The Pony Express only lasted a few months, or maybe a year, before the telegraph put it out of business. But they found that they were taking, I don't know, a 20-volt battery, say, clicking away with their keys. And the other end of the line, they were getting 40, 50 volts, 60 volts, whatever, you know, or nothing at all. And they couldn't figure it out. So they got some clever mathematicians on it, and they worked out the telegrapher's equations. And they only work in one axis, along one dimension. As soon as we've got more than a sixth of the wavelength dimension in 2 or 3 dimensions, we can't use equations. Except for very, very, very simple cases, some of which I'll give you in a few minutes. Anyway, so if we're dealing with something that's flat-ish, pretty flat like a PCB, without any tall components on it, we can use 2-dimensional analysis. Otherwise, if it's tall, we need 3-dimensional analysis. Now, these are based on Maxwell's equations, but as I said earlier, you can't use Maxwell's equations in real life because real life is just too complex. For instance, you know, how many products are built with infinitely long, infinitely thin wires over infinite ground planes? Very few, in fact. Reason being, they're very expensive to ship because they require an infinite amount of cardboard for their packaging. Anyway, what we have now, which we didn't have 40 years ago when I met my first EMC problem, was we have computer simulators. And they solve Maxwell's equations on very, very small little cells, smaller than 1/10 of a wavelength, where you can simplify them. So they solve simple versions of Maxwell's equations on a little cell, and then they do the cells joining it, and the cells are joining that. And the cells might be a millimeter on the side, and eventually they can do enough calculations to simulate a 10-meter cube or something. Just imagine how many that is. Anyway, let's look at, we're going to look at those 3 methods of analysis, but we have to, first of all, consider resonances. Now, everything, all circuits, have resonant modes, even accidental circuits, like caused by strays and things like that. Just like in the ordinary world, well, this is ordinary world, but in the world of, say, sound, everything has a different sound. If you tap on a window, or you tap on a bell, or you tap on a filing cabinet door, or whatever, it has a different sound. Well, that's its resonant modes, but they're acoustic resonances. Certain frequencies have a high gain, and so it gives the thing a characteristic sound. It's exactly the same in the circuit world. At these resonant modes, the currents and voltages experience a resonant gain, which is called their Q factor. It's not a TV game show, it's not X Factor or something like that, or Max Factor. It's not a lipstick. It's a Q factor. So Qs of 100 or more are common because we don't like to design our circuits to be lossy. We like our signals to run down a trace and appear at the other end. We like our power to go down a cable and appear at the other end. We don't like them to be lossy. So we end up with circuits which are actually rather resonant, like a bell, like a metal bell is resonant, okay, because they haven't got many losses. So gains of 40 dB or more are quite common in electronic circuits. When you get a voltage peak due to resonance, you get a current null and vice versa. The reason being, the energy doesn't change. The actual electromagnetic energy doesn't change. It's just that energy is voltage times current, or if you like, electric field times magnetic field. And when one is bigger, the other one has to get smaller to keep the same amount of energy. The reason we're interested in resonances is because we tend to get high levels of emissions and very poor immunity at resonances. The resonances can be caused in various ways, as we'll talk about in a minute. And so we often find ourselves controlling resonances to achieve EMC, good EMC. So looking at the lumped analysis, remember less than lambda over 6, we find everything has resistance, inductance, and capacitance, including all the components, wires, cables, PCB traces, connectors, bond wires, lead frames, even the silicon metallization. Okay, nothing escapes, including the stray or parasitic RLs and Cs. It's quite interesting to work out what happens if you've got, say, a 100mm long trace on a fiberglass printed circuit board that's bolted to a piece of metal. There's quite a significant capacitance there, and it modifies the resonant frequency of that trace. So you can find that just by moving a trace or a PCB closer to or further away from a sheet of metal, you can tune your emissions, the problems at which you have, the frequencies at which you have problem emissions, something like that. So we can talk about intrinsic RLC, like the self-inductance of a wire lead, and we can talk about extrinsic RLC, the stray capacitance or inductive coupling due to proximity to something else. And resistance. Poor old resistance actually has a frequency dependency because of skin effect. So we need to look at that. Resistance isn't as boring as it might have seemed. Now a DC current travels through the whole cross-sectional area of a conductor. Doesn't matter how big it is. It might be a 1 foot diameter wire. Never seen one that big, but a DC current would travel with the whole thickness of the wire. AC currents are forced to flow close to the surface. It's as if the metal is shielding itself. In fact, it's exactly the same effect. The metal is shielding itself, shielding its own insides. This is called skin effect. It's very important for shielding, but we're not going to talk about shielding today. What it means is that high frequency currents only penetrate weakly into the thickness of a conductor. Because they only penetrate a little bit into the thickness of a conductor, they don't travel through so much cross-sectional area, and so they see a higher resistance. We're not talking about inductive reactance here. We are talking about actual loss, actual resistance. If we imagine that sort of empty rectangle there is a copper sheet seen edge on, let's imagine it's a millimeter thick. A millimeter in thickness, and we're going to connect a battery to it, or DC supply, through a resistor to limit the current. We're going to make connections to either side of the sheet, like shown here. If we measure the current in there, we find that it has a uniform current density. If we were to cut through the sheet at any point here, we'd see that wherever we were in the copper, it had the same current density. If we were to look in the plan view on these contacts, we'd see there's some current crowding around the contacts, but here in cross-section, everything looks pretty much uniform. Now then, let's increase the frequency from DC to a megahertz. Just a megahertz, nothing serious. What happens is the current has to flow around the surface. And that's just at a megahertz, because the skin depth at a megahertz is about 0.07 millimeters. Skin depth is the depth it takes for the current density to drop by roughly a third, roughly 9 dBs. So 1 millimeter thick has 15 skin depths in it, so 9 dBs times 15 is about 145 dBs. Well, that means that nothing gets through. 145 dBs is a big number of dBs. No current really gets through. If this sheet was a mile wide and we connected our AC supply across the middle of it like this, the current still has to go around the edge to get to the other contact because of skin effect. Or, if you like, the metal shielding itself. As I said, one skin depth is a depth into the thickness of the conductor which the current density is reduced to 1 over E. This E here is that magic number that mathematicians like. I forget what it is. Its natural logarithm is the same as itself or something. Whatever. Who cares? It's a magic number. Here's the expression for the skin depth, delta, 1 over the square root of pi frequency mu naught mu r times sigma, the conductivity. You can also see versions of this in other places where they use resistivity, which appears on the top. Of course, resistivity is just the inverse of conductivity. Anyway, we don't like, to use this, you've got to look up all sorts of numbers. What's the permeability of copper? That's about 1. What's the conductivity? Well, I've worked it out for you. For copper conductors, the skin depth is 66 over root F, which means that the frequency in hertz gives you the skin depth in millimeters. That means that at 1 megahertz, we have 66 microns, and at 160 megahertz, which is another one I worked out once for some reason, the skin depth is 5 microns. Now, at that level, if you were to scratch the surface with your fingernails, you'd easily, with plain copper, put a scratch in that was 5 microns deep. You actually vary the resistance at 160 megahertz of that copper sheet. At 50 microns, 0.05 millimeters below the surface, what's that in inches? Oh, I don't know, not much. 10 skin depths down, you've got 90 dBs reduction in current density. So 50 microns below the surface, and we've got no current effectively. The current's traveling on the skin. I like to use graphs rather than equations, and for all the good conductors, the skin depth follows this sort of curve. There's a little bit of difference, aluminium, copper, silver, gold, zinc, tin. They're all pretty much along this line here, or this sort of line here. Things like titanium, exotic things like that are probably different. It's worth looking them up. RF Cafe has loads and loads of tables of skin depth for various materials. Anyway, what's that? That's A grade of mild steel. I don't know which grade, it's just an indicative thing. Mild steel is an alloy. There's hundreds and hundreds of different alloys, all with different characteristics, and they all have different skin depth characteristics. Down here, at low frequencies, the skin depth is smaller because of the mu r, the ferromagnetism. Up here, it's higher because the ferromagnetism can't follow the very high frequencies, and so it's lost. It has a frequency coefficient, and it goes away. And now we're left with just the conductivity of steel, which is not very good. So the skin depth is a bit taller, a bit more over here. I've tried finding out about these things for various grades of steel. It seems nobody publishes this data. The steel manufacturers don't publish this data. They'll give you the permeability down here, and they'll give you the conductivity, but they won't tell you anything about this frequency here. If you want to find out this, you have to get a sample and measure it yourself, sadly. Anyway, 50 or 60 hertz is about down here, so you can see that one skin depth in aluminium or copper, 50 or 60 hertz, is about 12 millimeters. In a typical mild steel, it'll be around 1.5 to 2 millimeters. So if you're going to do shielding for very low frequencies, you're better off with mild steel rather than you are with aluminium or copper. If you use heavily zinc-plated mild steel, you can get a good skin depth down here, and then you can end up along the zinc line along here, because all the current's traveling in the zinc, not in the steel. Anyway, that was resistance. It can catch you out. If you're designing, ooh, what happened then? Oh, I know. I pressed the wrong button. Hang on, I've got to go. Excuse me. I pressed the wrong button on my keyboard. How stupid of me. There we go. Right. Where was I? Now you're all sitting there thinking, stupid person. If I remember it, I'll tell you. Oh yes, I was going to say, catch you out. You can wind a high-frequency transformer with ordinary wire and find it gets too hot because the current in the wire is very high frequency and it's not traveling through, it's only traveling in the skin of the wire, so it's meeting much more resistance. You've got a much more lossy transformer than you're expecting. Anyway, still on lumped analysis, we have stray inductance. A thin wire has a self-inductance of about a microhenry per meter, or a thin PCB trace for that matter, about a nanohenry per millimeter. Now this assumes the return current path is a long way away. If you bring the return path closer, so you get some mutual coupling with the send path, then the mutual inductance cancels out, to some degree, the self-inductance. And this is one reason why we like to use coaxial cables or twisted pairs for carrying signals, because they have almost no self-inductance, because it's all cancelled out by the mutual inductance. When we're in close proximity to ferromagnetic materials like steel or ferrite or whatever, which have a permeability of more than 1, then our wire on its own will have increased self-inductance. But close proximity to a good conductor like a copper cable or some, aluminium metalwork, whatever, will decrease the self-inductance. And you can see that, for instance, with some alloys, like some grades of stainless steel, they're not very ferromagnetic and they're not very conductive, and you can actually have no effect on the inductance by putting your wire nearby. But that's a rarity. Looking at stray capacitance, a thin wire on its own in free space has about 40 picofarads per meter, or about 0.04 picofarads per millimeter. This is its space charge capacitance. It's capacitance on its own. People often forget that things have capacitance on their own. We think of things having capacitance if they're near to other things. 2 plates to a capacitor, but things have capacitance on their own. And if you have just a thing on its own, like a PCB trace on its own, put it near a dielectric like FL4, you're going to get more stray space charge capacitance, which means more current to charge it up when you change the voltage. If you have a conductor nearby, then we add extra stray capacitance, roughly at the rate of 8.8 over D nanofarads per square meter, where D is the spacing in air, and the square meters is, the cross-sectional area, if you like, that they're facing each other with. If it's a dielectric, if you have a dielectric there, then it's 8.8 times epsilon R over D nanofarads per square meter. Resonances in lumped analysis are caused by the inductive energy stored in inductances and inductive and capacitive energy stored in stray fields, or actual fields in components like inductors and capacitors. And all types of circuits have L and C, even if there are any strays. They cause resonances at 1 over 2 pi root LC. You will have heard that expression, or used that expression in the past. These little equations that I'm giving you are the only ones I use. If I need anything more complicated, I go to a field solver. So 1 over 2 pi root LC. The L could be the inductance of a trace. The C could be the stray capacitance to a metal box, or something like that. It's often very instructive to work them out because you find they're much lower frequencies than you might have expected. If there's any resistance in the circuit, these dampen down the resonances, so the Q isn't quite so high. Now we're on to transmission line analysis, which is for conductors which are longer than a sixth of a wavelength in one axis only. For these, we say a send-return conductor pair, we always have to take a pair, doesn't work otherwise, has a characteristic impedance called Z0. And the inductance and capacitance associated with a small length govern the velocity with which the waves travel through that length. It's 1 over root LC is the velocity, which is like 1 over permeability times permittivity that we had earlier. Sorry, 1 over the square root of LC. The ratio of L to C governs the characteristic impedance, root L over C. Compare this with what we had with permeability and permittivity earlier on. It's exactly the same. Now, the L and C values we use are associated with a small length, a per unit length. Depending on the wavelength, we might talk about per meter, or per centimeter, or per inch, or per millimeter. As long as the unit lengths we use are shorter than a sixth of the wavelength at the frequency that we're interested in. So, if we can keep the L and C from point to point in the same ratio, or the same values, and keep the Z0 constant from the source to the load, then almost 99.999% of the wave, or signal, or our power is communicated. Wow, wonderful. And we know this is matched transmission line design. What's that got to do with AMC? Well, think about it. If you've got all your signal or all your power transmitted from one point to another, and none of it is lost, you must have very low emissions. Okay? If you don't have a matched transmission line, then you're going to lose some energy, and you're going to have high emissions. So keeping the Z0 constant from the source impedance along the transmission line to the load impedance is called matched transmission line design. And it's a very inefficient antenna, a matched transmission line. Or as we'll talk about in our next webinar, a very inefficient accidental antenna. This is why, if you ever wondered, all general purpose RF test equipment has 50 ohm inputs and outputs connected with 50 ohm cable. Nobody really knows where the 50 ohm came from. It was just somebody's choice back in the dim, dark ages when they were discovering fire. And they stayed with us ever since. The telecoms guys use 75 ohms, again, because somebody else made a different choice for their equipment. It doesn't matter what the impedance is as long as you keep it the same. What if you change Z0 over dimensions greater than 1/6 of the wavelength? Well, these cause the propagating waves to be reflected. It doesn't matter whether the propagating wave is signal or power. And if you put a piece of wood, see a floating piece of wood in a pond, and drop your pebble in, and see the waves spread across towards the stick, you'll see they reflect off the stick. That's because the stick floating in the water has a mismatch, creates a mismatch in the surface tension, the surface impedance with the water. Same thing for EMI, or I should say electromagnetic propagation. We use this technique to create electromagnetic filtering, and also use it to create shielding. That's how we do it. We change the Z0. For filtering, we change the Z0 of the wave in the air. For shielding, we change the Z0 to the wave in the air. For filtering, we change the Z0 of the wave that's propagating along a conductor. It reflects the unwanted noise away from a protected circuit. Or in the case of emissions, it reflects the unwanted noise back into the circuit so it doesn't get into the main supply. We get resonances in transmission lines. These are not the lumped resonances at 1 over 2 pi root LC. They're all to do with the length and the wavelength. We don't get resonances if the transmission line is properly matched. But if it's mismatched, if we have a discontinuity at each end of the length of the line, doesn't matter whether they're too high or too low, they're the same type of discontinuity, we get resonances at a whole number of half wavelengths. We can say the resonant frequency is 150 little l over big L. Little l being an integer, 1, 2, 3, it's the number of half waves, big L being the length in meters. And that gives us the result in megahertz. So let's take an example of a low impedance output driving a short circuit. This might be a virtual earth amplifier or something. I don't know. It's a short circuit anyway. Maybe it's a capacitor at a high frequency. Here's the Z0 of our medium, which of course is higher than 0. So we have a low impedance discontinuity at both ends. Now watch what happens when we launch a wave into this transmission line from this driver chip. Whee. So what happened was the electric field started off at 0 because, of course, you can't have a voltage in 0 ohms. Went along, had a node at the 0 ohm end as well, and reflected back again antiphase, reflected back again antiphase, and kept doing that forever. We get what's called a standing wave. It isn't really a standing wave, it's ricocheting backwards and forwards at the speed of light. It looks like a standing wave though, because the peaks stay in the same place. The magnetic field is the opposite. It has a maximum at the ends, because in a low impedance, you're going to get a lot of current. Let me do that again. Okay. What about if the discontinuity is different at both ends? One's too high, one's too low. Then we get resonances at odd numbers of quarter wavelengths. We can say F-res is 75 little l over big L, but little l in this occasion is an odd number, 13579, so on. And it looks like this. Here we've got a fairly typical situation of a low impedance output and a high impedance load. And we get this sort of thing happening. So the electric field starts off with a node. Here it's a maximum, reflects back in antiphase, reflects back in antiphase. Magnetic field has a maximum at the 0 ohm end, so minimum at this infinite, the open circuit end. So we get a whole number of quarter wavelengths. Now other frequencies are frequencies where the length is not a whole number of quarter wavelengths, or in the previous example, a whole number of half wavelengths. We don't get a resonating conductor. Next time we'll see the resonating conductor is actually a wonderful antenna at its resonant frequencies. In fact, that's how they design antennas. What about two-dimensional structures? Well, we can make a guess at the resonances of a metal plate, for instance, with this formula 150, this is in air, 150 times the square root of little l over big L squared plus little m over w squared. Looks a bit horrendous as an equation, but it's really quite simple, because L and m are integers, 0, 1, 2, 3, and L and w are the plate's length and width in meters. So, for instance, here's a plate, and if we could see the magnetic fields at the 3 naught, that's 3 half waves long length and none across the width, then we can see we've got a resonance of 3 half waves. There's the 1 naught node. Magnetic fields, so of course they must be a minimum at the edge where you launch off into space, because this is a low impedance, this is a high impedance, so it's a minimum. We could have the 0-3 mode where we have 3 resonances across the middle. You could have the 3-19 mode where we have 3 resonances along the length but 19 resonances across the width, but I couldn't draw it. And let's draw the same thing for electric fields, which are a maximum at the edges. And if you have an electric field close field probe, this is the sort of thing you'll see at the edges of your PCB ground plane. What about a metal box? Well, we have a 3-dimensional version of this equation now. It's much the same. You see, a metal box or a metal sheet has to have the same discontinuity at both ends, at all of its ends, so you only get half-wave resonances. And if we can see inside our box, metal box or metal plated box, we see this. That would be the 3-0-0 mode, that would be the 1-0-0 mode. We could have the 0-3-0 mode, which is 3 across the width, or we could have the 0-0-3 mode, which is 3 vertically, or whatever. Again, we could have the 3-4-5 mode, but I couldn't draw it, make any sense. These are standing waves. And here is flow EMC. We saw flow EMC before, simulating a heat sink. It's actually now called microstripes. It's available from CST. Anyway, three-dimensional solver solving for a metal box with ventilation apertures in it. Notice how dotty it looks. These are actually the calculation cells that you can see. They're almost big enough to see. So each one of these is a calculation cell. And we slice through the box with this cutting plane to see what's going on inside it. We can see that we've, at the 3-0 mode, 3 resonances across the length, we've got very little leakage from these ventilation apertures because they happen to be in a region at this resonant frequency where the field strength is low. But on the end here, the field strength is high, and so we get more leakage from the box. People use these simulators to design simple boxes that are actually carefully designed to have the best EMC characteristics. Try doing this by making boxes and test them in a lab. You know, it takes months. But with a simulator, you can test this sort of thing in a few minutes and get a good box, good cost-effective box. Now, hang on a bit before I move on. Oh, no, we are finished now. Thank you. That's the end of today's webinar, and we have some poll questions.
Thank you, Keith. Unfortunately, we're going to have to skip the poll because we ran a little bit over on time, but we should...
Oh, sorry.
It's totally fine. We should have a call for final questions. Attendees, please enter any last questions you may have in the navigation pane, and we will try to get to some quickly. We have received quite a few inquiries on where to get additional information on this topic. There is a vast amount of content found on our website, interferencetechnology.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. Let's find a quick question. Keith, how do permeability and permittivity actually govern the speed of light?
Oh, the easy ones first, right? Well, the short answer is that I don't know. That's also the long answer. I think of it as being that because they actually store energy, as a wave tries to propagate through the medium, whatever, it's charging up these, what I think of as little inductances and little capacitances as it goes along. So it's sort of being dragged. So it doesn't travel at infinite velocity. It travels at the speed. It's like viscosity, It's like the medium is hanging on to the thing. So if anybody has a better suggestion or a proper idea rather than my half-baked ideas, I'd be very, very pleased to know. But that's the way I think about it. It's a bit like trying to run through, if you're up to your knees in the sea and you try and run, you can't run very fast because it's dragging on you. And it seems like the vacuum is dragging on the electromagnetic waves.
Great, thank you. We've received so many great questions that we will try to address in the future. Keith, thank you again for your time and expertise. Webinar attendees, if you have any more questions that we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, interferencetechnology.com. We will also send a link to all participants shortly. Thank you so much for attending.
Thank you.